Okay, can everyone see my screen? Okay, nice.
Yes.
So a quick bit of background on this paper. I think now it was either last week or 2 weeks ago. This year's NeurIPS took place, and I went through the set of spotlight papers. There was actually a ton, but like looking for ones that I thought might be interesting. And this was one of the spotlight papers. And so I don't know if evolving, when I first read the title, when I was talking about evolving patterns, actually I thought it was talking about like basically a dynamic relation, like a sequence that had a dynamic relationship, which was itself dynamic, and identifying that, meaning that like the dynamics of the system would change over time as well. One example of what that could look, actually, I guess there kind of is that, because the example I was thinking of is how you might have like a cyclical time series. So for example, people buy a lot more gifts during near Christmas in the UK. And so there's an example of like a time series whose dynamics changes over time. If you're looking at it in July, it's way different than it is in so yeah, I guess it is talking about evolving patterns that way, that those dynamics are changing over time. Anyway, so that's what this paper is about. I thought it has like 3 questions, which I think are really a good way to think about what this paper is about. So the open question that it addresses is identifiability of patterns in sequential data. And it's saying like we don't really have a lot of literature on this topic of like answering basically the 3 questions that are here. One is, how can the existence of evolving patterns in data sequences be determined? Which is basically saying, is there a pattern, or is the time series completely random? Because if it's completely random, then no matter what model you use to predict it, you won't be able to predict it. You like basically the past will provide no additional useful information to predict the future. And then it says, can one determine the historical span that significantly influences the current time point? That's another important question, with the idea that like how many time steps into the past should you take into account in order to estimate the future? Like what's the smallest number that you could use? Usually we use the Markov assumption, where we just say like the current state is all we need. But in a lot of places, there's examples where we're using a longer history. I think especially if you start going into like simpler models, it's like linear models, you can see using a longer time history more often. And then the last one is, how can we determine if the collected features are sufficient to reveal evolving patterns? So it asks this question of feature selection. And all of these are really hard. Like if you're using a neural network and you have 100 features, there's ways to determine which features the model finds most important for a given example or over a data set, but none of them are conclusive. Like we have ideas for how to do this, but it is quite a hard question to answer, even feature selection for the models that we use. So that's what this paper is about, trying to find a method where we can answer these 3 questions, which basically like means provides, and the way that they answer this question is they propose a way of measuring the quality of the relationship between the variables, like the history of the time sequence that you're taking into account, and then the variable that, like the future time step that you're trying to predict. So they want to measure that. And the way that they suggest measuring it is by using mutual information. And then they extend their analysis to an even harder problem, which is when you don't have time series with exact correspondences between time steps. And I'll get into what that means in a bit later. I actually think that part of it is the more interesting contribution of the paper, because a lot of the stuff I saw, I was like, I feel like I've seen variations on this theme before. But overall, yeah, so that's kind of what this paper is about. And then they have like a ton of experiments about kind of providing a proof of concept that their suggested method for answering these three questions actually holds water, that in experiments they see that this works. Okay, so let's talk about, I guess, sorry, one final thing. How should I do this? What I'm going to do, just to make it a little bit easier to understand everything, is actually first describe the two problems that they try to approach, and then go into like the background on mutual information and optimal transport, because I think that might help provide a little bit more context. So the first problem that they're trying to tackle is quite an easy one, which is that you have a time series with big T time steps, or maybe not quite an easy one, quite a simple to define. Can be incredibly complex to actually solve. But a time series of vector data points with dimensionality big D, and you want to estimate those three questions for it. So it's like, how predictive are the past states on estimating the future state for this one time series, for this one really long time series? But then they have a second formulation, or second problem that they approach, which is the one where it's called measure evolving patterns without correspondences. And for this problem, it's not that you have a single sequence with big T steps. It's instead you have samples from different time sequences up to big T steps. So what that means is that like you don't have correspondences between samples that you have for different steps. So the example that they give is medical data, without going into a lot of detail, but I can kind of see where they're going. It could be like, so say you have 10 patients where they each have a heart disease, and you measure, you take them in for a diagnosis once at different ages. So it could be like you have a patient that comes in at 40, and you take an MRI of their heart, and then you have another patient that comes in at 46, take an MRI of their heart, and your data set ends up being 10 data points from 10 different ages, but or maybe at the same age for some of the times, but you don't actually have a correspondence because you only take that MRI for that person once. And so the question that they ask there is like, the problem they address there is like, how can we still answer these questions when there's no correspondences between the samples in our data set? So I consider that a much harder problem, and we'll go over the approach they take. But hopefully that will give you guys an idea of, hopefully that will ground some of the stuff we talk about later. So let's talk about mutual information, because this is like the basis of all of their work. This is like the main idea for all of their work. So as I said before, they have these three questions. They're trying to answer them by providing a way of quantifying the predictability, or like the strength of the relationship between the history of variables and the future, like the history of a time series and its future. And they want to use mutual information as the metric that they use to quantify it. So here you can see like the abstract definition of mutual information, maybe like the mathematical, but there's no maybe, or the formal definition, and I don't know what's the correct word, but anyway, what it is so it's the KL divergence, which is a distance measure between two probabilities, between the joint distribution of two variables and the product of their marginals. And the less information that X provides about Y, the smaller the mutual information will be. I think that's correct. Well, I guess it depends if yeah, thanks. So yeah, the more mutual information, the larger this value will be. So thanks for the confirmation. And so yeah, and then they say, like, the reason why I said this is the formal definition. Yeah, there we go. The reason why I said this is the formal definition. So there was just a comment for any, and I'll read it out so people can know, which is overall a value of 1 for mutual information equals complete dependence, and 0 equals no mutual information. So this is, as I said, like the abstract definition of the metric, but doesn't really tell you how to calculate it. So they provide a little bit more detail by saying that instead of using this abstract version, we're going to use the estimator below. So this is, when the fact that they say estimator means it's an estimate of mutual information, not the actual mutual information. But I guess there's probably some math that shows that they're close to each other. The reason why it's definitely an estimate, though, is because, so what you can see, it's like the expected value of M for the joint distribution minus the log of the expected value of the exponential of M for the marginals. So what's M? M is a M is a critic function, which means that it's something that the person who's calculating mutual information decides. Probably there has to be some, maybe M has to meet some constraints as a function. But actually, if it says that it's using a neural network, I don't even know if it's true. It's saying that there's past work where they use a neural network to estimate M. But so this is the estimate of mutual information that they use throughout the paper. And then later on, they go on to define what they propose M to be. And that's more, I think, the contribution of this work is like saying what M should be and then providing some theory around that. And now, if you have correspondences between time steps, so if you have like a single time series where you know all of the elements in the time series are related to each other, you can calculate mutual information using this metric. But when you don't, it becomes a lot harder. And then they suggest using optimal transport to solve an optimization in order to calculate it. So and then they give a very, very general formulation of optimal transport, like the optimization that you have to solve to determine like the optimal transport to solve the optimal transport problem. Optimal transport, I hope I don't butcher this definition, but the optimal transport of a distribution is like basically what's the smallest transformation you can make to a probability distribution to get from one probability from an initial probability distribution to a target probability distribution. If you were here last week, we saw a lot of examples of optimal transport in Ben's paper because, like, basically it was drawing a line between like the means of two Gaussians, and it was a straight line versus other approaches which were like more of a curve, because the optimal transport between those two means is a straight line instead of anything that curves. Yeah, so that's what optimal transport is. And let's talk about their proposed method. So their proposed method, again, is like we're measuring the quality of a relationship using mutual information. So like, how do we calculate mutual information? Like, let's give enough detail and then justification to actually be able to do it in practice. So the first proposed method, it's addressing a problem where you have a single time series and a vector data points, and you want to estimate the evolving patterns or estimate the goodness of fit. Let's see. So if you remember, the only thing that was missing from this definition up here is M. So we have to say, like, what is M for them? So for them, the definition of M is they define a look back period, or like look back number of steps, which is K. And then what they do is they learn a function, or they learn two functions, and then the M is a combination of those two functions and a norm, the L2 norm. So the functions that they learn are, so you, by the way, one of my complaints about this paper is I feel like they could have done a lot better at standardizing the notation. Like here, I would have just used the same variables they're using down here, because I feel like it's a little bit confusing, or at least make this X. But so each X1 and Y, they're all elements in your time series. So they're all Z's in their proposed method. This, by the way, this is what M is, just so we can look at this equation while I'm talking. And so the two functions that they're learning are G and F. G is an encoding function, and then F is an aggregation function for the history of, well, basically it translates like the history, or like the look back number of steps that you're, number of vectors that you're looking at, into a single vector that's the same size as one time step. The same dimensionality as a vector from one time step. So G, the reason why G exists is actually because you might be using a very high dimensional time series, like say you're looking at images. Then, and like the images that they use in the experiments, the dimensionality is something like 1 million dimensions. It's close to that, and that makes, they argue that makes the search space of solutions like way too large, and it's really hard to quantify mutual information there. So like, let's take an encoder that embeds these into a much lower dimensional space. So G is an encoder that can basically lower the dimensionality of the input. For most of the experiments, actually, where they have very low dimensional data points, they use an identity function. They don't even learn G, and you could take it out of this equation. But they have to put it here because for high dimensional stuff, they do use a G. And then F, like I said, would be another function that just aggregates the history, like a neural network. In experiments, they use an LSTM. So they would just go through the last K steps and then take the vector that comes out of the end of the LSTM and use that. And then they take the squared difference between the two, which is the L2 norm. So this is what M is for them. And they calculate mutual information. This looks like a lot of different variables, but if you just like substitute M into here, M for what you see here, you'll recover this. So this is how they calculate mutual information. Now they have two proofs, or no, sorry, they have two points. I actually think they're previously proved. Like I've seen this result in other papers before. But anyway, they have 2 points that they make about their method. Now, one thing that I think took me a little bit of time to understand is I was like, is this the training objective? Is like evo rate is the training objective? It's not the training objective. It's actually just, like I said, a measure of the quality of the relationship, or the and the way that they're to make this work, to make their math work, they propose that you use MLE or MSE to train your model. So your model is a combination of these two functions, G and F, and then you would use MSE, which is actually what this is. or MLE, which is, so MSE is mean squared error, MLE is maximum likelihood estimation. So my maximum likelihood estimation, you'd also be estimating the, you'd have some uncertainty parameter or parameters that are part of your estimation, whereas MSE would just be estimating the mean of your distribution. And actually, I'll just scroll down to the second proposition because that's exactly what it's saying. So I've seen this, but yeah, if anyone has a question, then go for it.
Hi, sorry, I had a question. Why is there a minus sign before M?
Good question. Why is there a minus sign? Probably, okay, so if there wasn't a minus sign, the larger the error, the larger this value would be. And so maybe the larger the mutual information would be based on the equation that they're using. So they put the minus sign in, so the larger the error, the smaller the mutual information is. So that like you get a high mutual information when there's like a good relationship, and when there's a small error, and a low mutual information when there's a high error. That's my guess. Arvid, did you have a question?
One question was, do you know why we have the...
I know, you cut out.
Sorry. Do you know why we have the logs and...
So why is there a log here, I think is your question. I think I'm guessing here, but I think it's just like a unit conversion. There's probably a really good reason for it mathematically. I don't know what it is. I haven't looked into this estimator before, but if you didn't have it, this is like taking the exponential of M and then the log of it. So if you didn't have it, then the difference between these two things would, like, this would be in different units than this would be, or like, because you'd have taken the function and taken it to an exponential. That's the explanation I can give. I don't think it's a great explanation, but that's why I think they've done it. Yeah.
Hi, sorry, can I ask a stupid question? Why do we need mutual information instead of correlation?
Okay, not a stupid question at all. Again, maybe I'll just say this for now, and then you can. Everything I say is my opinion. I always like. I'm never completely sure, or often not very sure. But so, correlation measures, or at least usually the way it's defined, it usually measures a specific type of functional relationship between two variables. So like the common correlation coefficient that we usually calculate is actually just testing for linear relationships between two variables. So like if you had a nonlinear relationship and you calculated, and that was very strong, and you calculated the Pearson's correlation coefficient between two variables, you could get a value of 0, even though they have a high correlation. I think mutual information is more general because it's looking at it in like in the realm of shared information, and so you don't have to make assumptions about what the functional relationship is between the two variables. That's my guess. I'm just thinking in the back of my head though that like in order to calculate these things, you make so many assumptions about like the underlying distributions that I could be wrong, but that's my guess.
Can I jump in? So the mutual information as opposed to correlation, if you're using correlation like a Pearson correlation, that's based on ordered data, which requires a linear relationship, or at least a monotonic relationship of some kind. And if the relationship is in any way not monotonic, like for example, you have a circular relationship between X and Y, then, I mean, a circular relationship will have 0 correlation. But clearly there is a relationship between the two, a circular correlation, as in if you have a line of points in a circle on a graph, would have high mutual information, but low Pearson correlation. Okay. There's another kind of thing. So you could have a distance measure. So you could use something like Euclidean distance between the two data sets. versus Euclidean distance within a data set X
Mm.
and a data set Y, and use the relationship of those would give you the same kind of thing. So you could have proportional Euclidean distance variation. That's a similar thing to mutual information, just a slightly different approach to taking it.
Yeah. Sorry.
Yeah. And then, sorry, just to answer the log thing. So the equation for calculating the probability, the joint probability mass function, looking at the word Wikipedia part, includes log. So that's why the log is in there. And I think it's part of it making it unitless, because otherwise you'd have the units of X and Y, as you said.
Okay. Thanks.
But
I might start deferring
It
questions to
shouldn't
you.
really matter. That
Sorry, Arvid, go ahead.
the unit should matter, I think, because the logs and the exponentials essentially more or less cancel the unit. I would have thought the second part about this definition is that the
Arvid, you're cutting in and out.
screw it. Yeah. Fine.
Yeah. Feel free to still ask questions. I'm just going to tell you if you're cutting in and out. Maybe we'll hear them. Okay. So the second proposition that they have, which is one that, like I said, I've seen before, and I actually think it's a really good one to know, just to give you some idea, is because I think when everyone trains a model, when people train a model with MSE, they call it a prediction, which it is a prediction. Like the output of the model is a point value or point estimate instead of like a probability distribution. But you could view it as a probability distribution where it's like the probability distribution that's being outputted has a variance of 1. Like basically it's this distribution here where the output of your model is a point estimate, and your variance or your covariance matrix is an identity matrix. And that's one of the two that estimates. So even when you're doing point estimates, you could of like a continuous value, you could view it as doing uncertainty estimation, or it's a form of maximum likelihood up to a constant. So that's the second thing that they show. But then the first thing that they show is just how you can decompose maximum likelihood estimation into, I think this is what you would like. This is model uncertainty, epistemic uncertainty versus aleatoric uncertainty, also called data uncertainty. And they talk about a couple of different points here. I actually didn't find any of the points that they I'll just finish what I'm saying, and then I'll read out a comment. I actually didn't find any of the points that they said here like super, like I didn't exactly understand what was so important about what they were saying. I think the only thing I could say is maybe they're just justifying their result. Like basically, I think what they're doing here is they're showing that mutual information. Maybe here, what they're doing here is they're showing that mutual information is part of this equation and how it's related to maximum likelihood estimation. And then what they're doing is they're showing like how even if you like, I'll just read it out down here. So if you could say, conversely, proposition 1 reveals that even if F can properly learn the true probability P, its expected risk remains high when there's no temporal dependency that can be leveraged. I is small. So yeah, it's showing the relationship between mutual information and likelihood, maximum likelihood estimation. Now, there was a comment, I'm just going to read it out. It said, I would have thought the crucial part about that definition are the distributions in the expectations. Once where X and Y are sampled together, and once where X sampling is independent. from the marginals only. The latter destroys any relationship that X and Y have, and thus would constitute a good baseline of the expected entropies. It's an interesting comment. I'm not going to go too far. I'm not going to go into it now, but we can pick it up a little bit later. I just want to make sure I get through everything. Okay, or most of it. But if you have any comments, feel free to interrupt me and just tell me what I'm saying wrong, or not saying correctly. So the second problem that they look into is the one I described before. So instead of having a time series of vector data points that are related to each other because they're all part of the same system, you have samples from all part of the same system, and they evolve, like one evolved from the other. That's it. You have samples from time series, multiple different time series that all come from the same system, but they have no correspondences between them, or at least you don't know the correspondences. You don't know if one of the points you have for time t is related to a point that you have for time t plus 1. And they over here they talk about how you could calculate mutual information in this context. And they create a definition for mutual information, which is the one you see here. And then what they do is they basically do what I would call like a form of expectation maximization, where they alternately update f and pi, where pi is like the joint distribution describing the two variables, and then f is the function in here. I have to say, if anyone has a better understanding of what's going on here, please let me know, because I didn't exactly understand this. Like, I don't understand what pi is because I feel like it's never defined. And then when I look in experiments, I couldn't understand what pi was. Let's just go through it slowly to see if anything pops out. Okay, so they're saying that they estimate, I can kind of see this. So this is their optimal transport function, and they need to estimate the joint distribution between like time zt and time zt plus 1. And they do it by like fixing f and then calculating p, and then fixing pi and calculating f. Again, one thing I don't understand is that this is something that's done at test time. This isn't a training method. This is to calculate the mutual information. And I'm surprised that f and v aren't fixed. Yeah, if anyone has any comments, please say them. And I'm sorry I can't explain this better, but this is a way of estimating the mutual information where they estimate the joint distribution between two time steps. One crucial thing is that zt and zt plus 1, they're probably not from the same, they're probably not corresponding to each other. So zt plus 1 didn't come from zt. Yeah, that's the big problem that they're working on. Okay, so here's how they calculate the mutual information with this definition. But again, I don't see how they calculate pi. I don't understand how they calculate pi star. I mean, I understand it here, but what is pi star? They don't say it's a function. I mean, I know it's a function, but they don't say what it is. And in the experiments, I also didn't understand. There was a comment.
I think I might be wrong on this, but I think this is the mutual information. Like, as in, we're not calculating mutual information, we're setting it as a learnable outcome, I think.
Yeah, so this is pi, or this is the estimate of mutual information, but they have to estimate pi star in order to calculate it. And I'm wondering how they estimate pi star, and like what is it, a model? Like, is it a neural network? Is it like, what is pi star? All it says is that pi star is estimated using the optimal transport optimization, and that they also estimate f when they're doing that.
No, I'm stuck. Yeah. This is almost within reach, but not quite.
I looked at it for like maybe 10 minutes trying to figure it out. Couldn't really figure it out. But hopefully you kind of get what's going on. Hopefully you get it a little bit, like as much as I do what's going on. Anyway, let's keep going because we don't have a ton of time and there's a lot to cover. So then they have some results. One is that like, and the results were, even these results were a little bit fishy to me, because they were saying like in machine learning prediction tasks, there exists an optimal function where the conditional distribution zt plus 1 given zt satisfies this. And I was like, I don't really think this is true, because why would every single conditional distribution between two variables in a time series be a normal distribution? But there must be something I'm missing here, because this was very, like, this was peer reviewed by 4 people who know better math than me. But anyway, all it's saying here is that there's some optimal function, so a function that can estimate the mean really well. And then they say that if f attains f star, so like if you can estimate f star with f, so the function that you're using to estimate f star is like you can get it, then the estimate of pi star that you get from doing optimal transport is the joint distribution between the two of them. Then they give some example that I don't really feel like is a good example. But again, here's another one where I was like, okay, I guess this is true, but yeah, this doesn't make sense to me. It'd be great to have one of the authors to talk to, as always, with these papers. But what they're trying to show here is basically that with this optimal transport approach, you can identify the correct joint distribution, which means that you can correctly estimate mutual information. That's why these propositions are here, or these results are here. Okay, let's talk about experiments. Now we got through the part that I don't think I could explain very well. So they have a ton of experiments. Almost all the experiments are on synthetic data sets that they've created. And so they're almost all proofs of concept. So the first data set that they have, so it's sequential data with known correspondences. So you have a data set with large T steps, and the data generating function is, you can see it here, it's zt. So this if you look at this is an average. So it's rho times an average plus 1 minus rows, like times noise, white noise. And this is rho is a correlation coefficient because it's between -1 and 1. They choose a dimensionality of 128 for the Gaussian that they're sampling from, and they say that the optimal function is average. And they have quite a few different results related to this. So basically, they're not training using mutual information, but they are calculating mutual information as they train. So in all of these examples, this is, I don't know if this is a training set. Actually, it probably doesn't matter for this toy example, but like, actually, anyway, they have a sequence and they change row over time. So I guess they're just feeding in data over time. They change row over time, which changes the mutual information because, as they say over here, you can calculate the mutual information for this example. When they say the ground truth information, not mutual information, I think they mean the ground truth estimate of mutual information based on the formula they gave. But it's this that you see over here. And so over training steps, they are changing the mutual information and they're showing how the estimate of the mutual information changes as they change this with their model. So their model, again, G, the encoder is an identity function, F is a LSTM, and they're training it using either MSE or MLE, probably MSE. And you can see that it really quickly jumps between between these points. Now that they have, instead of using MSE, sorry, between the different mutual information, so it's pretty good at getting to the different mutual informations, except for this really high one. Just took this wrong. So for this experiment setup, they have a couple of different results besides this. This one's like, okay, our method works pretty well. Here they're saying, what if we didn't specify the critic ourselves as like the error between the square error between the estimate and the ground truth, and instead we learned a critic, which is something you see in the past literature, and it shows that like these learned critic functions are quite poor at estimating mutual information correctly. So yeah, it's a justification of their definition of mutual information. And then over here, okay. Okay. Over here they have estimating. It's evil rate W. Okay. So here was the normal evil rate calculating mutual information. Here's where they have optimal transport as part of the problem, and they're using evil rate W, and then for G, C is using the identity function, and D is using a neural net. So they're just showing that, again, you get a pretty good estimate of mutual information, even when you're using evil rate D for a situation where the problem set has where your time series is has correspondences between it. Then, all these results, they have a second data set where each time step, like you still have T points, but each time step is from a different sequence. And you have this as your data generating function over here. And as I say, like the optimal function is F star, what you see here. So the optimal function for them to learn is F star. And they show how they perform. Where is it? The results are in, in one C and D. Oh, so never mind. Yeah, these aren't from the same. These are from two different data sets. That's actually kind of confusing. I don't think there should be the same figure. There should be a line between here, because I didn't realize that these were from, the first two are from one data set and the second two are from another. Anyway, moving on. Oh, so all they're showing here, like I said before, is that you can get a good estimate of mutual information. So proof of concept results in both of them. Next, they talk about the whole questions that they were trying to figure out before, which are identifiability. Let me just check the time. Okay, we're good. So how do I know how many data points to estimate? How many data points of my history to use, or what dimensionality, or like what features are important? And I actually feel like the example they gave is a little bit hand wavy, because I'll show you the results and explain why it's a little bit hand wavy. So here is for this data set that they're talking about down here that has it's a fifth order data set with a dimensionality of 5. And they don't say it over here, but they say it somewhere else, that the fourth feature is redundant and the fifth feature is irrelevant. So what they are showing here is they're saying like, okay, the higher the mutual information, the better. And then so if I get the highest result with like k equals 5 and num feet equals 5, that means that I can identify these trends with mutual information, like what's the best order and what are the features. So over here you can see that the mutual information increases until you get to k equals 5, and then they argue that it decreases. So everything with k more than k equals 5 is less, but that's not what I'm seeing here because it looks like k equals 12 is higher, but they're all close to each other. So at least maybe you wouldn't be able to say how many steps you should take into account, but you can lower bound it. So you can see that I need at least 5 steps. And then for number of features, they say, like, as you can see, the best performing mutual information is the one with 3 features, because those are the only 3 relevant features. Okay. Again, I feel like these results are pretty close to each other. But I guess if you just take the maximum, in this case, it is 3. And then finally, another result that they have, which we'll go into, is that they do like a video prediction task where they switch frames, they swap frames in the time series to add corruption, and then they want to show, and so the more corruption there is, the more switched frames, the less like actual relationship there is between frames. So you can see that like the mutual information is best when there's 0 corruption and is worse when there's 0.5. So it's saying the mutual information does decrease as we add like noise of some kind or another to the distribution. But I was thinking to myself in this point, like, how would you use that number? Because you'd have nothing to compare it to, in the sense that, like, if you just had a data set and calculated the mutual information for that data set, how would you know that it, like, the level of corruption in that data set? Like, how would you be able to measure?
Are they including that just as a proof of concept, as in like, look, when there is less mutual, we can see that it is working appropriately because we're getting less.
Yeah.
Do you think that's what they're doing?
What? Okay. I didn't hear the last thing you said.
Just, do you think that's what they're doing?
Oh yeah, I think it is a proof of concept. Sorry. And from that perspective, it definitely works. It's more just like to make this practical. I was wondering how you use the information. Over here, I can see, because these are hyperparameters of the model that you're creating. But over here, I'm like, this is not a hyperparameter. Sequential data. We talked about that. Okay. How much time do I have? Okay. I'm just gonna go through the rest really quickly because I actually felt like there was a lot that should have been explained here. Like, for me, I don't know, maybe it's not important to know, but all these results start talking about this data set, starting from here. It's called like M4 monthly, and they tell you that they have some metric where smaller is better, but I have no idea what M4 monthly is. And basically what they're trying to show is that this is like the state of the art for estimating forecastability or like predictability, and that Evo rate is like way more consistent in terms of estimating mutual information. So there's times when like the forecastability goes up, but the performance goes down, and vice versa. So that's why they say that, okay, forecastability, Evo rate is better than forecastability as a metric for this. But I wish I knew what M4 weekly was, and especially because in these results over here, where you have, I don't know what M4 is, and they're saying that like our method is better because mutual information is higher with M4 daily and weekly than it is for monthly. I'm like, well, I don't know what M4 is, so I don't know if that makes sense. multivariate time series. Maybe M4 is just the number of time. Okay, anyway. So their last result, which I'm sorry I'm going through so quickly, but I'd rather have a little bit of time to for questions or finish early, is that they want to talk about how evo rate works with the existence of evolving patterns. So like, I guess there's some periodicity in M4 that that's maybe like on a daily or monthly or weekly basis. And the question is like, how much is it able to capture like what this periodicity is? So evo rate shows higher values for M4 daily, consistent with experimental results in which M4 daily achieves lower SMAP. So it's saying that using a daily periodicity is the best. And so the fact that daily is less than monthly makes sense, whereas for the forecasting one, that doesn't happen. And then I won't go into these other two because even the reviewers say like this needs to be defined if for people to understand. So yeah, that's the paper. Hopefully you found it interesting, even though I couldn't explain it that well. But I thought it was cool. And I know I did say some things about it that like I'm a little bit critical. But as a proof of concept and introducing some really cool ideas, I think it's a great paper. In terms of being very practical, I don't know if it's there yet. But if anyone has any questions or things they want to say, now's the time.
Well, thank you for bringing it to my attention. This is something I've been looking at recently, and I hadn't come across. I don't know, I just kind of skipped out mutual information and found a distance metric, whose time as a distance component. But this is interesting. It's good to think about. So,
yeah, for sure. I always like when I always secretly hope that the key to better machine learning is just like loss functions, or stuff like this, because that means it's about viewing the problem differently, which I think is a really interesting way of looking at stuff. But anyway, trying to view the problem differently. Thanks everyone for coming. I'm just going to the top real quick. Thanks everyone for coming. We don't have paper club for the next week or 2 weeks. I think for the next two, let me just check real quick. Okay, yeah, we have paper club in 2 weeks on the 2nd of January, but we don't have paper club next week. So I hope everyone has happy winter holidays, and I hope we'll see you back here in 2 weeks. Thanks for coming.
Merry Christmas. Bye.